In part 1 of this video series, we learned that visualizations can provide big picture insights into the behavior of a quantitative variable, including its central tendency and spread. In part 2, we'll explore how we can specify these properties using numerical summaries. Along the way, I'm going to describe in words how these summaries are calculated. Even if you never calculate these summaries by hand, it's helpful to know where they come from. First, to assess the central tendency of a quantitative variable, that is, what's a typical outcome, we can utilize measures such as the mean and median. Both of these have units on the original scale, but are calculated differently. The mean is the average of the data points. It's calculated by adding up the values of the data points and dividing this total by the sample size, that is, the number of data points. To calculate the median, we sort the data points from smallest to biggest and identify the middle value, that is, the 50th percentile. Now, in our bike data, we had observed from our plots that daily ridership tends to be around 4,000. Numerical summaries provide more precision. Here, note that the mean ridership was roughly 3,656 rides per day, marked by the vertical line here. And similarly, the median of ridership was 3,662 rides per day. Now, as a consequence of the roughly symmetric nature in the ridership data, the mean and median values here are quite similar. Essentially, there's no skew in our data points that pulls the mean away from the median. This won't always be the case. There are also various approaches to measuring the spread or variability in ridership from day to day. A quick summary is provided by the range of values from the minimum to the maximum. In the bikes data, we observed as few as 20 riders per day and as many as 6,946 rides per day. These extremes are helpful to know, but we also want to narrow in on the variability within this bigger range. To that end, we can calculate the standard deviation. Roughly speaking, the standard deviation measures, on average, how far values fall from the mean. Or, per the term standard deviation, it's the typical or standard deviation of values from the mean. These distances from the mean, hence the standard deviation metric, has units on the original scale. For example, bike ridership varies with a standard deviation of 1,560 rides per day. Or, on average, daily ridership falls 1,560 rides above or below the mean ridership. Essentially, the standard deviation, we're always looking at comparisons to the mean. How far do values fall from the mean? We'll get more practice interpreting standard deviation throughout the semester, but putting it on the scale of our data can be helpful. Notice that the majority of our data points fall within one standard deviation of the mean. That is, on most days, ridership is in the range of 3,656, our mean, plus or minus 1,560. Further, almost all, not quite all, but almost all data points fall within two standard deviations of the mean. That is, on almost all days, ridership is in the range of our mean, 3,656 rides, plus or minus 2 times 1,560. For a deeper understanding of standard deviation, we have to address the variance metric. Yet another measure of spread, variance is equal to the squared standard deviation. Thus, standard deviation is the square root of variance. Roughly speaking then, if standard deviation measures how many units values tend to fall from the mean, then the variance measures how many squared units values fall from the mean on average. To calculate the variance, we measure the squared distance of each data point from the mean. Then we add up these squared distances and we divide that total by the sample size minus 1. The fact that we're dividing by sample size minus 1 instead of just the sample size means that we're technically not averaging the squared distances from the mean, but we're doing something very close to that. Further, the fact that we're working on the square distance scale means that the variance metric has squared units. For example, daily ridership tends to fall 2,434,399 squared rides above or below the mean ridership. Now, if you're thinking right now that the squared units makes this variance calculation tough to connect to our data or context, I definitely agree. And that's why we'll typically measure spread using standard deviation, as it's on the same units as our data. I'm going to conclude this video with some formulas for calculating some of our numerical summaries. For the purpose of intro stat, these formulas are optional. Thus, if you're interested in the mathematical details behind our work, and/or you may go on to study more statistics or other quantitative fields such as mathematics, physics, economics, etc., please stay on the video. Otherwise, feel free to stop the video. To begin, suppose we have a sample of n data points represented by y1, y2, up to yn. The mean of these data points is represented by y bar. To calculate y bar, we sum up the y values and divide this sum by our sample size, n. The last part of this equation here shows the calculation in shorthand notation. We use the sigma notation to represent a sum, and so we're summing up yi values for I equals 1 up to I equals n. And then we divide this sum by sample size n. Next, recall that the variance measures the typical squared distance between y values and the mean. Thus, to calculate variance, we take the squared difference between each y value and mean y bar. So y1 minus y bar squared, y2 minus y bar squared, up to yn minus y bar squared. Then we add up these squared distances and we divide by the sample size n minus 1. Or in shorthand, we sum up the squared differences between yi and y bar, where I ranges from 1 to n. And again, since we're dividing by n minus 1 here, instead of dividing by n, this variance calculation is close to, but not exactly equal to the mean of squared differences. Finally, the standard deviation is calculated as the square root of the variance. The standard deviation thus converts this variability metric to the original unit scale. But again, given the square root transformation and the use of n minus 1 in the variance formula, we cannot interpret the standard deviation to be the actual average or mean distance between y values and the mean. But the idea is very close.